Assalamualaikum warahmatullahi wabarakatuh, and hi again. We are still in simple linear regression and correlation chapter, but in part 3 this time, which focuses on correlation and simple linear regression analysis using Microsoft Excel. Let's look at these part 3 learning objectives in the next slide. These Part 3 learning objectives are listed as follows. At the end of listening to and learning from this video, you should be able to first obtain and interpret a correlation coefficient that measures a linear relationship between two quantitative random variables, that is, in particular, between the independent variable x and dependent variable y in this chapter, where x and y are quantitative variables. Second, you should be able to also perform a simple linear regression analysis and finding the correlation coefficient by using Microsoft Excel. What's the difference between a simple linear regression model and a correlation coefficient? Both methods can actually be used to investigate or learn about the relationship between independent and dependent random variables. But again, what's the difference between these two methods? Recall what simple linear regression model is. It is a model or equation that relates one single dependent or response variable y to another one single independent or predictor variable x linearly. Or we can say the dependent variable y can be a function of the independent variable x if there is a linear relationship between the two variables when the slope parameter is not zero. In simple linear regression analysis, instead of having y as a function of x, you can also have x as a function of y if x is the dependent variable, whereas y as the independent variable. However, please note that a regression equation of y on x is not the same as the regression equation of x on y. Therefore, you need to be very clear which variable is independent and which variable is dependent. Correlation coefficient, however, is not a model or an equation or even a function. Rather, it is a single value that measures the strength and direction of a linear relationship between the two variables. If we use R to denote the correlation coefficient for x and y, then R for x and y is just the same as R for y and x. Let's focus on the correlation measure. You may refer to Statistics for Engineers textbook on pages 162 until 166 for detailed explanation. For population data, the correlation measure, which we call it as correlation coefficient, is commonly denoted by a Greek letter called rho, whereas for sample data, the correlation coefficient is commonly denoted by R, where R for two continuous or quantitative random variables is precisely a Pearson's product moment correlation coefficient, or simply a sample correlation coefficient. Another type of correlation coefficient can be a Spearman's rank correlation coefficient, which can be used for rank or qualitative data, but this is not covered in this course syllabus. Now back to sample correlation coefficient R, its possible values can only go from -1 to +1. How do we interpret the value of R? Let's look at the following list. As R value goes towards or becomes closer to +1, it implies that the linear relationship between the two variables is getting stronger in positive direction. Similarly, as R value goes closer to -1, it implies that the linear relationship is getting stronger as well, but in negative direction. However, if R moves towards 0, either from positive or negative direction, the linear relationship is said to get weaker. Furthermore, if R is equal to 1, we have a perfect positive linear relationship, whereas if R is equal to -1, it indicates that we have a perfect negative linear relationship between the two variables. If R value is 0, it means no linear relationship between two variables exists, or the relationship is non-linear, such as a quadratic or cubic relationship may exist between the two variables. If you compare plots of points on a scattered diagram, you can say that the wider or more scattered the plotted points are, the weaker the relationship is, or the closer the R value is to 0 from any direction. That is, R value becomes smaller. In contrast, the narrower or less scattered the points are on a scatter plot, the larger the R value is, or the closer the R value is to positive or -1. If all points are exactly on a straight line, then you have R equal to 1 or -1, indicating a perfect positive or negative correlation. By formula, the sample correlation coefficient R is given as the sum of product as xy divided by the square root of the product of two sums of squares for x and for y. In fact, this formula is provided in the statistical table booklet, page 4. To interpret the value of R, you must comment on two important points. The first important point is on the direction of the linear relationship. Is it positive or is it negative? The second important point is on the strength of the linear relationship. For example, is the linear relationship weak, such as R equal to 0.3, where the xy points are widely scattered on a scattered diagram? Or a moderately weak relationship, such as R equal to 0.6, with a still wide scatters on the diagram? Or do you have a strong linear relationship between x and y, such as R equal to 0.8, where the points are narrowly scattered on the scatter plot? Or maybe you have a very strong relationship between x and y, such as R equal to 0.9 or 0.95, with much less scatter amongst the points on the scatter diagram. You can have a similar interpretation of strength for negative linear relationship. Therefore, please comment on these two important points when you are to interpret the value of R. You can also obtain the R value directly from your scientific calculator. Please refer to example 7.3 again on page 150 from the Statistics for Engineers textbook, where the sample data were given as follows. After inserting all this sample data into your calculator, for 570 MS model, you can use the following operators to get the value of R given as negative 0.9395, which is correct to 4 decimal places. What can you interpret or infer from this R value? You may say that based on the R value, there is a very strong negative linear relationship between x and y. Again, in the interpretation here, you must mention the strength and direction of a linear relationship between x and y. Please refer again to the sample data from task 7.4 question 2 from the Statistics for Engineers textbook for another example. Recall that this task question is on the relationship between the number of defective components produced by a machine denoted by Y and the machine speed denoted by X. The sample data were given as follows. The question this time is, you are to find the Pearson product moment correlation coefficient, which is the sample correlation coefficient denoted by R, and interpret your answer, which is the value of R. By using a formula, you need to calculate the sums of squares and the sum of product first, as calculated before and shown as follows. Substituting the values of sums of squares and the sum of product in the formula of R, you should get R equal to around 0.9611, which is correct to 4 decimal places. You can also obtain the value of R directly from your scientific calculator and see that the value is exactly the same as the value calculated by using the formula. You may want to ask, which approach should you use to find R? Is it by formula or is it by using the calculator directly? Well, the answer depends on the question you have. Most of the time, when you're given a data set like in this example, you can directly use your calculator to get the R value. However, sometimes the data are not given directly, but some statistical summaries are provided, such as the sum of x, the sum of y, the sum of xy, and so on. Or sometimes, the question purposely asks you to find the R value by using a formula. So in these two cases, you must use the formula to calculate the R value. Now, having obtained or calculated the R value, what's next? Of course, you must interpret the R value. So, for this question, since R is 0.9611, which is close to 1 in positive direction, then you can interpret that there is a very strong or highly strong positive linear relationship between the number of defective components produced by a machine denoted by Y and the machine speed denoted by X. This interpretation does in fact tally with the conclusion on the existence of linearity between the two variables when you tested beta in the previous part 2 video. Another point to remember, since R measures a linear relationship between two variables, so the word linear must be clearly stated in the interpretation of R, in addition to the strength and direction of the relationship. Now we move on to learning the technique on using the Microsoft Excel to perform a simple linear regression and correlation analysis. You may refer to section 7.8 in Statistics for Engineers textbook, pages 166 until 171 for the detailed steps and procedures on using this technique. In this video, you may refer again to the sample data from task 7.4 question 2 on the relationship between the number of defective components produced by a machine and the machine speed. The procedure to use Excel is as follows. First, get your Excel worksheet and insert or store the given data column by column in the worksheet like this. Next, click Data on the menu bar and then in the Data menu, click Data Analysis. If you do not have the data analysis in your worksheet, you can add in the data analysis toolpack as explained in chapter 6 video. Now, after clicking on the data analysis, the data analysis pop-up menu will appear like this. Choose Regression for simple linear regression analysis and click OK to proceed further with the analysis. Let's look closer at the data analysis pop-up menu. Here, for the input information, you need to input the range of y values by dragging your cursor at the column of y values including the label. Similarly, to input the range of x values, you can drag your cursor at the column of x values including the label. Since the first row is label, then you need to click the label here. For confidence interval, by default, Excel provides a 95% confidence interval for the intercept and slope parameters. You can change the default value of confidence level to 99%, say, if you want to get a 99% confidence interval for beta by ticking this box and modify the confidence level here. For the output option, by default, the output will be located at the new worksheet ply within the same file, so I do not intend to change the output location. Next, you may be interested to check the model assumptions by choosing the normal probability plot to check the normality assumption and the residual plot to check if the residuals or errors are randomly scattered with constant variance. More importantly, you can also choose the line fit plot to get the scatter diagram of observed and predicted or fitted points as well as the fitted regression line. Check again at the data analysis pop-up menu. Please make sure that the Y and X input range are already inserted. The label and confidence intervals are ticked and modified if necessary, and other required plots are already ticked before you click OK and get the result or output immediately afterwards. After you click OK in the data analysis pop-up menu, you will get this Excel output immediately in the new worksheet ply, which contains the summary table, the ANOVA table, and the T table, as well as all the plots chosen earlier. I need to remind you that Excel gives you the output only, but when you want to perform a complete analysis, you must provide the complete statistical hypothesis test procedure as you did manually before, such as writing the hypothesis statements H0 and H1, writing the decision rule, and making the decision and conclusion accordingly. Let's look at the output more closely in the subsequent slides. From the Excel output on simple linear regression analysis based on sample data from task 7.4 question 2, let's learn what those values are in the output. You may want to check the sample size first to make sure that you have inserted the correct value of X and Y. So you should have 10 observations. So let's look at the sample size here. Well, it is 10, and in general this is n, which is the sample size. So we can proceed further from here. The coefficients here are the estimated intercept alpha hat and the estimated slope beta hat respectively. Therefore, the fitted or estimated regression equation can be written like this. The estimated standard error, which is the standard deviation of the errors or residuals, is given by around 6.5937. If you square this value, then you get about 43.4765, which is the residual or error mean square MSE used to estimate the error variance sigma hat squared. Since we only focus on the slope parameter beta when making statistical inferences in simple linear regression analysis, then we can look at the confidence interval and possible hypothesis testing on beta. For the confidence interval, the output provides the 95% confidence interval for beta to be around these two values. And since we specify a 99% confidence interval in the data analysis pop-up menu, then Excel also gives us the 99% confidence interval for beta, which is a little bit wider, given by this range of values. Now for a hypothesis test, the information from the Excel output allows you to perform a statistical test on the existence of linearity, or to test the significance of regression where beta is different from 0 and H1. So you can use a t-test approach where the t-test value for testing beta is given here, which is around 9.84. You can also use an f-test approach where the f-test value is given here, which is around 96.92. To write a decision rule, you can use either the given p-value in the t-table here, or to use the significance f-value given in the ANOVA table here. Please notice that both p-value and the significance f-value are exactly the same. So you can either reject H0 if the p-value is less than the level of significance alpha, or you can also use this statement, which is to reject H0 if the significance f-value is less than the level of significance alpha, at which you perform the statistical test. Now, what about the correlation coefficient R? Can we get the value of R directly from this Excel output? Of course, yes. That is through a multiple R value. Since the estimated beta is positive, then the multiple R value is exactly the correlation coefficient, which is the R value. But if the estimated beta is negative, then the value of R will be negative multiplied by this multiple R value. So in general, the R value is the sine of beta times the multiple R value. What about this R square value? Let's find out the answer in the next slide. Let's look at what R square is. It may sometimes be called as the coefficient of determination, and by formula, R square is defined as 1 minus SSE over SST, where SSE is the error sum of squares, which represents the unexplained variation in the data, and SST is the total sum of squares, representing the total variation, or simply SYY. You can also check that this R square value is also the same as the square of the sample correlation coefficient R. Based on this formula, we may say that the R square is a statistical measure of fit that indicates how much variation of a dependent variable y is actually explained by one or more than one independent variables in a regression model. In other words, R square describes the proportion of variation in the response data that is explained by the regression model. The value of R square can go from 0 to 1, or usually quoted as a percentage from 0 to 100%. Now let's look at the Excel output based on the sample data from task 7.4 question 2 again. You can see that the R square value is about 0.9238, which indicates that there is about 92.38% of the original uncertainty in the value of y can be explained by the straight line model. Therefore, in this example, you may say that the simple linear regression model in this task question is adequate to explain the relationship between the number of defective components produced by a machine and the machine's speed. If the R-square value is low, say smaller than 60%, you may question the adequacy of the simple linear regression model. Important note to take is that please be cautious to use the R-square value as a measure of model adequacy if there is more than two independent variables in the model, such as in a multiple linear regression model, because the value of R-square always increases as the number of predictors or independent variables in the model increases. But that does not necessarily tell us that the model is more adequate or better. You may refer to advanced references for further reading and information. What about the plots obtained from Excel output? You can refer again to the Excel output based on the data from task 7.4 question 2. Two plots can be used to check the model assumptions. First, you can use a normal probability plot to check the normality of a response variable y as shown here. If you click on the plot, the chart element box will appear like this. Click the plus sign and tick on the trend line. Then a straight line will appear on the normal probability plot. What can you infer from this plot? If the points on this normal probability plot are scattered randomly around and close to the straight line, then you can say that the normality assumption of the response variable y is satisfied. For this task question, looking at the scattered points around and close to the straight line, you can say that the normality of the response y variable is satisfied. The second plot is the residual plot to check the normality assumption of the errors or residuals, shown as follows. You can check if the plotted residuals or errors are randomly scattered around 0 with constant variation. If you can notice from this plot, the residuals seem not scattered so randomly and has a specific pattern of down and up. So you may question the normality assumption on errors based on this sample data. Maybe more data are needed or some transformation is required to overcome this issue. Remember, in practice, you must always make sure the model assumptions are satisfied before you can use the fitted model for prediction purposes if the parameters are estimated by using the least square method. Otherwise, if the assumptions are not satisfied, then your prediction may be questionable. You may use an alternative approach, which does not depend on the normality assumption, such as to use a robust technique to estimate the regression model parameters, which is beyond the scope of this course syllabus. From Excel, you can also obtain the scatter diagram with plotted, observed, and predicted y values as shown in the following line fit plot, where the blue dotted points are the observed y values, whereas the orange dotted points are the predicted or estimated y values. You can use the chart element editor as well to obtain the predicted straight line of y on x given by y hat equal to negative 16.6914 plus 0.2614 times x for the task 7.4 question 2 example. We are at the end of this part 3 video. Hopefully by now, you should be able to achieve all the previous part 1 and part 2 learning objectives. Whereas at the end of learning the topics covered in this part 3 video, you should be able to achieve the 2 learning objectives set out at the beginning of this video. So we finish with the last chapter 7, which marks the end of the SSCE 2193 Engineering Statistics course syllabus. Thank you very much for watching. this video and other previous videos patiently. Hope you can stay focused and are able to digest the content delivered in every video. Until then guys, Assalamualaikum warahmatullahi wabarakatuh, and I wish you all the very best in your exams and future undertakings. Bye for now.